Hello all. This presentation is to address what exactly we mean by system calls. So we are going to refer some manuals related to various Linux commands, as well as we already have discussed few of these during the regular classes. So let us try to understand what exactly system calls are. So when we do deal with OS, to access the system resources, we have two different mechanisms. Now these mechanisms will help us to access the resources. So first mechanism is by making use of different modes of execution, and second mechanism is system calls. Now, when we deal with first mechanism, we need to address one important terminology called kernel. So when we say OS kernel, it is set of modules or subsystems which are used by operating system to support various functionalities. So and it is basically core, or maybe you can say heart of the operating system. And when we do talk about kernel, there are the total space is divided in different groups like user space and memory kernel space. So above the hardware layer, you can assume that there is a kernel space, and outside the boundaries there will be user space. So when your user wanted to access hardware, that can be accomplished by making use of system calls, which definitely will be going through the kernel space. So for that purpose, let us understand these two modes. One is called as kernel mode, and other one is called as user mode. So when we do deal with user mode, in this particular mode, the processor will be executing the normal programs or the executable statements written in the user's program in normal way. So it may not require any help of operating system to execute it. When I say may not require, I'm addressing with respect to what are the activities which may not require directly access to hardware units can be done. Say for example computations. And when we deal with kernel mode, ultimately we are talking about execution of both normal and some privileged instructions, which would be, when I say privileged instructions, I do mean by the instructions which are trying to gain, or which would be used to gain access of different hardware resources. Now to achieve this, processor would be making use of different additional registers supported with the architecture, as well as the amount of memory space which is specifically given or can be accessed using only in kernel mode. When we say user space would be kind of space in memory where user will be permitted to execute his programs, and this space will be protected. This, when I say protected, when one user is executing, other user may not be permitted to enter into that area. In other sense, one can say when your one process is executing, other process cannot interfere with the execution of the process. Now, if at all I am trying to access a user process, then I am working as a kernel process. Now, when we do talk about kernel space is a space available in memory where only kernel processes will be running. The main operating system process will be running, and user has to access these by making use of system calls only. Now when I say system calls, let us try to understand this particular picture. So when user writes a code, he would be writing a code by making use of different library routines, and those library routines are executed in the user space. For example, I am using a printf statement in my code. Now this printf is executed in user space, but when I do talk about trying to access the standard output device, my printf may not gain directly that access. So I have to execute the write system call, and that write system call would be dispatched or executed through syscall process in the kernel space, and appropriate kernel service would be used to achieve the goal of printing for a while. whatever was the message added by the user in the printf statement. Now then suddenly we need to address this particular question. Why do we require at all the system call? This would be a mechanism using which we will be asking kernel to do something for us, because kernel will be owning the complete hardware, and whenever user program wants, say for example, to print hello world, user program cannot print it directly. It has to take help of the kernel process so as to gain access of standard output device and achieve the goal, whatever the goal that was desired goal for this case, printing the hello world. Now let us see this one. Say for example, user is trying to write, say in this case, let us say that this is printf. When I do talk about xyz, let us say this is printf. Now this printf would be having in a standard routine library, say for example libc library, there would be a system call, and that system call is, say for example, write. Now when that write system call is replaced for printf, which we saw through strace, ultimately in kernel mode the code associated with the write system call would be executed through the system call handler, as well as the associated routine, service routine, what we referred earlier as interrupt service routine or system call service routine, would be exactly executed at that point of time, and then appropriately the return things would be done, and user may see when the printf was written, the actual work of printf is done at that place. So it is shown here in the same way. So user would be writing programs through library, and this is written in a user space. Then library calls the system calls, which helps us to interact with the kernel and in the kernel space by making use of different drivers associated with the device. For example, when we do deal with, say, standard output, then we need to gain access of that particular standard output device. So that would be achieved through the routine, service routine. So that's what we mean here as a device driver for while. So when we do deal with these system calls, every operating system will be having its own mechanism to provide this. So in Windows it is generally referred as interrupts. In Linux it is called as system calls. So that doesn't change the meaning or working of both of them. As we have seen, rather, the programs, every program may not be allowed to access system resources directly, and that's why they require help of OS to interact with that device. Correct. And associated services which are supported by operating system for this case through set of functions. So these functions will be called as system calls. Right. So these are few properties of system calls. Say for example, when we say system calls, they always run in kernel mode. When a system call is executed, the arguments for this call are passed from user space to kernel space, because when we deal with write system call, we already saw that we have to provide a file descriptor, the message, and a length. So these will be picked from the user space and then will be passed to kernel space. At that time, when it is done, this is achieved, the user process suddenly becomes a kernel process when it executes the system call. And this is done by executing special instruction like trap or software interrupt. So in assembly code, I showed you int 0x80 command or instruction, which causes this special switch from user mode to kernel mode. Right? And when the system call completes the work, again the reverse process starts to be done. Like we need to go from now kernel space to user space, kernel program to user program, and then the program would be running user mode. So for example, one can see these all system calls available in this directory. So we already listed all of them. Like here I am specifically writing unistd32.h underscore 32. So if you wish, you can definitely see the 64-bit 2 by replacing 32 by 64. So the system calls should be provided for each of the service which is supported by your operating system: memory management, process management, networking, right, file systems, and so on. So if I see, there would be a system call interface where all these services related to process, memory, file, devices, and networks, these are the subsystems created on kernel, and the features should be implemented internally through the software support. So there could be multiple drivers written. So process management may try to access only the CPU. Okay, this is architecture dependent code definitely. Virtual memory, like memory management routines would be using, or by making a virtual memory, would be accessed through memory manager. It will be accessing memory. File system, then you would be talking about disks and CDs available, different block devices. If at all you are talking about devices, like for example standard outputs, standard input, then consoles, character devices. And if at all networking is required, then you have network subsystems where you will be interacting with the support drivers for the network interface. So these are some sample system calls for files and input output: open, close, create, unlink, read, write, L6, chmod, and so on. Similarly, for process management, we will be seeing that in next session: fork, exec, exit, wait, sbrk, etc. Similarly, there can be for the system calls used for inter-process communication: sig action, pause, sig send, kill, etc. Now, if at all we need to understand, say for example, the system calls, you can see them listed into unistd_32.h, but the functions to use for system calls as a normal function can be listed, or are listed into this unistd.h file available in user input. This is again the sample example given with respect to what kernel space and user space, how interaction is done.